we can indeed start on time. So thank you, everybody who took the effort and trouble to come through the snow and through all the slings and arrows of outrageous fortune which are aimed against us at the present time. I'm just going to say a few words about Judah, but let me remind you, this set of JILA colloquia is aimed at the entire JILA community, including staff and students, possibly especially staff and students, and everybody else like myself who would love to know what the heck is going on around here. And we hear people get prizes and we don't know why they get those prizes. So we're hoping to have a shared event here in our attempts to get back to normal. Here's for a slightly better 2022 going forward. If you look at the clock, ask yourself, where did that come from? Came from Judah.
Yes, indeed.
I used to think that the person who did time on your computer or did time on your clock was some set of people at NIST, maybe 100 of them. But no, it was one person, Judah, who had the vision that the world needed a clock, not just one of those clocks that works with enormous precision, but something that the rest of us can use. And it was Judah that did that. Judah came to JILA in 1967 to work with Jan Hall. 2 years later, he was hired into NIST, and he joined the Time and Frequency Division. He started thinking about important things like people need clocks, ordinary people like you and me. And he's been with us ever since. And he is still, I would say, the major player, one of the major players, gradually handing it off to some of the other folk, but he remains a key member of people who are trying to figure out what time is and how it should be kept and how it should be shared with the world. So thank you, Judah. You have 40 minutes.
Okay.
And there'll be 15 or 20 minutes of questions
Okay.
at the end. If you are remote, which many of you may be, Tyler at the front is monitoring the chat. And if you have a question, you can, and Tyler thinks it's a good one to interrupt, we'll ask to interrupt. Okay. Thanks, Judah.
Shall I turn the lights down a little bit? Is that easy to do?
There you go.
Excellent. Okay, well, thank you for coming and for staying here in the middle of the snowstorm. What I wanted to do was to give you some insight into atomic clocks and how they work. And so to begin, let me give you what I would call a generic clock. Okay, so there's a device that generates ticks. It's some kind of periodic event, and I count those ticks, and I may divide them so I don't count every one. I may count every other one or every some number. And then I use those ticks to drive a display. And there are two pieces of the clock that are really, one of them I'm not going to talk about at all, which is the distribution system. That is, given that you have the time, how do you distribute it? And so we have a whole bunch of distribution systems that Andrew kind of mentioned. We have a network system that gets 1 million requests a second. And I'm not going to talk about that. That's a whole story all by itself. The thing that distinguishes, for example, pendulum clocks from atomic clocks is that in a pendulum clock, the periodic tick generator and the reference frequency are the same thing. That is, the pendulum length and so on specifies the period, and it also drives the clock. But in cesium clocks and atomic clocks, as we'll see, that's not the case. There are two separate devices. There's a thing that provides the reference and a thing that provides a signal. Okay, so now I have to remind you of some jargon in case you find yourself at a time and frequency cocktail party and you need to show that you really are inside. First of all, when we talk about the time of a clock, what we're really saying is we're talking about the time difference with respect to a second device. And so if we say the time is plus 1 second, what that means is that the time of this device that we're talking about is ahead of the reference clock by 1 second. And it's often common to imagine that the reference clock is so much better than the device on the test that any variation in what we see, we ascribe to the device on the test because the reference clock is super duper wonderful. Now, the second quantity, of course, is frequency, and the frequency is the rate of change of the time difference. So that if the frequency is positive, that means that the local clock on the test is running fast. And if the frequency is negative, that means the local clock is running slowly. And it doesn't have anything to do particularly with the internal workings of what actual frequency is used inside of the clock. Okay, now, the common unit for frequency is in nanoseconds per day. And it's kind of obvious what that means. A clock with a frequency of 1 nanosecond per day is gaining 1 nanosecond per day with respect to the reference. But since nanoseconds and days are both units of time, I can convert 1 nanoseconds per day to seconds per second. And if I do that, it's about 10 to the minus 14, more or less. And so it's 10 to the minus 14 seconds per second, which is usually referenced as just 10 to the minus 14. And everybody understands that 10 to the minus 14 without any units at all means 10 to the minus 14 seconds per second, which means about a nanosecond per day. And that's a typical unit. Yes, sir.
Why on earth do you call it frequency?
I'm sorry?
Why is it called frequency?
Because I said so. The answer is, if you want to have the jargon of a field, you got to accept the jargon of the field. And this is the common, I agree that frequency has units like 5 megahertz or 10 megahertz or whatever megahertz, but this is the way, if you look at frequency, if you go to a time and frequency colloquium, you're going to hear frequency referenced this way.
But they didn't choose it randomly. There must be a reason.
I'm sorry, I can't understand you very well through your mask. Maybe we ought to just, you can ask me just later. But the answer is, I introduced the slide by reminding you that this is jargon. Okay, it's the way the word is used. Now, for extra credit, okay, what you will find is that the word offset is used both for time and for frequency. And so people talk about the offset of a clock, meaning the time offset and the frequency offset. That screen just went away. Okay, now in quantum mechanics, frequency has a special role. The transition between two states is associated with the frequency, and the difference in the energy has this relationship with the frequency. And so that the minute quantum mechanics was developed, and because frequency has a special role in quantum mechanics, everybody immediately said, aha, it's a good way for making a reference for a clock, because it has a frequency which is characteristic of the properties of the atom or the molecule or whatever, and that's an invariant in principle, blah, blah, blah. And so it ought to be a clock. And so that idea existed very early in the quantum mechanical business. Now, it turns out, of course, this idea works for any atom in principle. That is, the characteristic of quantum mechanics is not unique to any particular atom. But when you actually get down to it, it turns out that it is easiest to deal with hyperfine transitions in the ground state. And what that means, for those which that means, is that I have an atom, and I look at the outermost electron of that atom, and I look at the situation where the nucleus and the outermost electron have spin down, and then compare to the nucleus and the outermost electron have spin up. And that's kind of a uniform idea of what the easiest way to make a clock is. Now, that's not the only way. And in fact, if you look at the new generation of optical clocks, that's not the way they work. But in all of the microwave clocks that we've talked about, that's kind of the system that was used. It's a spin flip in the ground state. Now, if you went to a graduate student in 1960 or 1961 or 1962, when I was a graduate student, and you asked that graduate student, how shall I make an atomic clock? Okay, now this is not the faculty, this is the lowly graduate students. And you'd ask them, okay, graduate student, in an atomic beams laboratory, like where I worked in NYU, how should you make an atomic clock? Well, the answer is, first of all, you should want to have a situation where the atoms are isolated. You don't want them to be affected by collisions or by interactions or whatever. You'd like to have atoms in as pure a state as possible. And what that meant in 1950 or 1960 or 1940 even was an atom in an evacuated tube. We're going to have a beam of atoms in an evacuated tube. The idea of slowing down atoms, all that stuff came later. And in the 1950s, a vacuum at the time was 10⁻⁷ torr, which is kind of bad by JILA standards of today, or even by JILA standards of the later era. But in fact, it's good enough. And the reason it's good enough is that the cross-section for collisions is such that on the average, an atom in a beam is not going to collide with anybody else, provided the apparatus is less than a few meters long. And so if I make an apparatus that's, let's say, 5 meters long or 4 meters long or 3 meters long, the probability of a collision is essentially small enough that I can neglect collisions even at 10⁻⁷ torr. So that it was good enough. So that's the first requirement that a graduate student would have told you. Second requirement, you want to make a beam of atoms which is easy to produce and easy to detect, because you don't want to have a research project with the generator or with the detector. And when you go to an atomic beams laboratory and you ask atomic beam graduate students what atoms to choose, the answer is easy. It's atoms in the column 1 of the periodic table, the alkalis. There's no periodic table here, okay? But those turn out to be super duper easy to make beams of them, and it's super duper easy to detect them. Now, that's not a quantum mechanical principle, that's a quantum engineering principle. It says that it's much, much easier. You don't have to have a research project to build a detector. Okay, next principle. Okay, the atoms should move as slowly as possible. And the reason they should move as slowly as possible is if the atoms move more slowly, you have more time to look at them. And now you take all of those requirements together, and what do you find out? Cesium. So cesium was the obvious winner for what you were going to make a standard out of. Okay, and any graduate student, and when I was a graduate student, any graduate student would have told you that. Okay, it was obviously the right choice. Okay, so we've honed in on what it's going to be. It's going to be a ground state hyperfine flip in cesium, in which I take the outermost electron and the nucleus from this state to that state. Okay, now, on the other hand, I have to tell you that we have to award honorable mention, and the honorable mention has to be rewarded to rubidium and to hydrogen, because there are engineering issues. And Peter Bender was one of the ones who talked about the engineering issues of rubidium, and Norman Ramsey was one that talked about the engineering issues of hydrogen. And in fact, both of those states, both of those atoms still exist. But from the official point of view, cesium is the winner. Okay, so now with that idea in mind, let's talk about an atomic clock. So there it is. There's a bunch of atoms which I see in the lower state, and I shine some energy onto them, and the energy is a variable frequency oscillator. I can tune the oscillator to do whatever I want. And now I tune the oscillator until I find that the atoms go up to their upper state. And I say, aha, that's the right frequency. I've now set the oscillator to match the frequency of the transition in that particular atomic state. And so what I do is I lock the oscillator. I now feed back that fact into the oscillator and lock its frequency so that its frequency is locked to the transition frequency, in this case of cesium. And that's the atomic clock. And now I need to deal with some practical issues. And then the practical issues is that that frequency turns out to be a relatively high frequency. So I'm going to divide it down by some number, and I'm going to produce an output of 1 pulse per second. And of course, once I have an output of 1 pulse per second, I drive a clock. And so I drive a clock with that tick, and that tick is derived from an oscillator that is locked to cesium. Now, one of the important questions is, okay, now that you've done that, how many cycles of that frequency are going to match 1 second? And what I want to do is I want to be sure that I don't produce a sudden step in the length of a second or in time. And so I want to match this frequency as best as I can to the astronomical standard of frequency, which was a thing called ephemeris time. And so in 1955, Essen and Parry, who built the first cesium clock in the UK, and William Markowitz, who was an astronomer at the Naval Observatory, got together to measure the question of how many cycles of cesium should go into a second, such that it matched as closely as possible with the astronomical definition of a second up till that point. Okay, and what they did was it's actually a very clever experiment. Okay, I mean, Markowitz was a very clever guy, but you can neglect that because you have to ask yourself, Markowitz is in Washington, D.C. at the Naval Observatory. Essen and Parry are at the National Physics Laboratory in Teddington, Kenny. And so you got to compare the two. It's a long story. It's a very interesting story. Okay, but 3 years later, they publish a paper, and what they decide is that the divisor for cesium should be 91926317770 cycles exactly, 0.000. Okay, and that was a number that Markowitz, in fact, it's published in Physical Review Letters. I think it's published in Physical Review Letters, Volume 1. Okay, and so that number, and after a long time, that number became the officially accepted length of the cesium second. And that is still the officially accepted length of the cesium second. On the other hand, you have to ask yourself, are you sure about that? And the reason is because I was a graduate student in 1960, 1962, and there was already grumbling about that number. And the grumbling fell into two states. There were two categories of grumblers. The first category of grumblers said that the number was too small, that in fact, a better estimate of the number was somewhat higher. And in fact, if you look at Norman Ramsey's book, which is a Bible at the time, he, depending on which page you look at, he suggested that the right answer was something like, instead of 770, something like 800 or maybe 830. And so that was the first group. And that group said that the data should have been analyzed differently. There was a systematic offset in the data, and the number should have been larger. And the second group was that, never mind what the number is, Markowitz could not have done it that well. That there were more digits in that number than can be justified from the experiment. And now, I mean, you can read, there's all sorts of discussions about this. You can look at my own papers. There's a very interesting review article. If you're interested in the question, you can decide, you can look at the thing, and you can decide for yourselves. But the fact of the matter is that that is the number. And so we have decided by international agreement that that is going to be the length of the cesium second. And as I say, there's an enormous discussion for some other colloquium about what are we going to do about that? Or should we do anything about that? Or is the disease okay? And would the cure be worse than the disease? And that's a time for some future colloquium.
Out of curiosity, how precisely were people talking about things in terms of seconds at that time?
So before the definition of cesium, would people be like, I'm gonna publish in a paper to 6 digits of frequency with the units of hertz, or
you could do, okay, previously, if you were prepared to do an average for a long time, you could do a part 10 to the 9th.
Okay.
And the part 10 to the 9th came from a very lengthy average against an astronomical observation, because the astronomical observation was the definition. Okay, now we could have a slight discussion maybe at the end about what that really means, because it has some of the same characteristics of the definition of a meter. Okay, namely, there's a group of people who decide something, and then they go off to Versailles and they drink champagne and blah 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 blah. And now there's all the practical metrology people who are left with the incredible headache of, well, how do I deal with this? So that's yet another colloquium. Okay, how do I actually do this?
but if someone had published something with 12 digits and claimed it was in hertz, or
I think
they would have been laughed out of the room, because they would have said, how could you possibly know that?
If you were at the 10 to the -9 level, you were doing very well. Okay, but that's but in fact, it was hard to do 10 to the -9. the NBS standard, well, this is going to take a long time, okay? But this is something for the coffee table, right? But the question of what the standards committee do and to go off to Versailles and drink champagne about, and what actually happens in practical metrology, those are not necessarily the same thing. Okay, there's all these interesting questions okay, but we'll talk about that. Okay, but here we are. Okay, now let's talk about the fact that, in fact, let's go back to the real world. This is all what you might call theoretical atomic physics. Everybody said, oh boy, this is wonderful, blah, blah, blah. But now we go back to the question of practical metrology, and we're going to build an atomic clock. And why is it that atomic clocks are not perfect? Well, first of all, the problem is that what happened here? Okay, there we are, real world. Okay, so of course, the problem is that the atoms, although we started out with the idea that the atoms were going to be isolated and so on and so on and so on, they're in fact not isolated in practice. There are electric fields, there are magnetic fields, there are collisions. There's all sorts of sad stuff. And that sad stuff perturbs the frequency. It means that the frequency that we've very carefully done is not quite the frequency of the transition as derived from some wonderful quantum mechanical calculation. Okay, and what we'd expect is a static frequency offset, and we'd expect that there would be a slow frequency drift because these things might change in time. So that's the first bad news. So I've introduced to you bad news department number 1, but that's not the end of the story. Bad news department number 2. Okay, of course, I ought to point out to you that it's going to be different for every device. Bad news department number 2, the lock loop, the thing that detects that the transition has happened and locks the frequency, well, that's going to have some noise in it. There's going to be some electrical noise in that loop. And that electrical noise is going to be fed into the variable frequency oscillator, which means that the variable frequency oscillator is going to have noise, which has nothing to do with the atoms. It comes from the lock loop. And under the best of all possible circumstances, that's going to be white frequency noise. It's going to be a random fluctuation. But what it means is that the output is going to jitter, which has nothing to do with quantum mechanics. So this is a second problem. It's real world part 2, but we're not done. Okay. Let's suppose that I measure the time difference. And what I want to do is I want to estimate the frequency, okay? And I want to see what happens because the clock has frequency noise. So I measure the time difference at some point, and now I say, let me try to predict given that I've measured it at T1, what is the time difference going to be at some future time, T2? Okay, well, there's T2. And now remember, what I've assumed at the moment is that the problem is frequency noise. Okay, well, I don't know what the frequency noise is going to be. And that means that between T1 and T2, the frequency noise has some value, which I've shown by all those various arrows, so that the value at T2 is going to be somewhere along that line. And I don't know where it is. That's my prediction. But now T2 arrives and I make a measurement. And when I make the measurement, what I discover is that's what's happened. And now, so first I was speaking as a prophet, and then I was speaking as a historian. But now I want to do this again. Given that I've decided what happened at T2, I want to ask what's going to happen at T3? Well, at T3, the same thing's going to happen. I'm going to have white frequency noise again. And again, the time is uniformly distributed about that point. And so what's happened is that at each point, the white frequency noise introduces what's called in the trade, okay, a random walk, which means that at each point, there's some random walk that happens to the next point. And then at that point, there's another random walk that happens to that point. And that random walk has a variable size because it could be any one of those things. Now, so what I've decided is that the future time difference, that is, if I speak at any time as a prophet to what's going to happen at the next time, it's uniformly distributed about the current time. Okay, it's not like it's uniformly distributed about some global mean. It's uniformly distributed about the current time. And what that means is that the mean value does not exist. So that you've got to be very, very careful because there is no mean time difference. A random walk has no mean time. It kind of wanders around. Okay, well, life has its problems, it has its problems, but I'm not done yet. Okay, so let's talk about the real world part 3. Okay, the real world part 3 is that this divider, which is so wonderful, has some jitter connected to it. And that jitter means, here it is. It means that this line, this is the signal, and when it crosses the axis, when v equals 0, I'm going to generate a tick, and that's my divider. That's how my divider works. But the trouble is that remember that there was some noise in the divider too, just like there was some noise in the frequency loop. And what that means is that the noise obscures the zero crossing. It means that I can no longer decide exactly when that zero crossing is. And in fact, I have some variation, okay, which I've shown kind of schematically here, which means that although there is a true value for when the tick occurs, my actual measurement of the true value is going to jitter back and forth. And that jitter back and forth, I assume, because I feel like I can't handle it any other way, is that the noise and the signal are not correlated with each other. So that if I make rapid measurements over and over and over and over and over and over again, my noise is going to jitter about the true value. And that what I'm going to assume, and what turns out to be a reasonable assumption, is that in fact, okay, the time difference is uniformly distributed around the true value, okay, and that the mean value of that time difference is the truth. Okay, now, for those of you who are interested in statistics, you can try to decide what the actual distribution of these data is. It's not obviously Gaussian. Okay, it is true that it has a random process, but it is a random process that's not Gaussian. But that's just something for somebody to think about. Okay, the trouble is that in the real world, if I'm running a time service, averaging is not possible. When the bell rings, I have to produce a time, and I have to produce a time every second. And the fact that I could average and produce a better time, well, that's all wonderful in principle, but that doesn't help me in the real world. Because in the real world, I have to deal with a tick right now. I can't average and say, well, the average over 10 ticks is worth something or other. So that means that real world life has problems. Now, let's ask what happens if I now try to estimate the frequency in the presence of this kind of noise. So that the way I'm going to estimate the frequency is I'm going to see what the time difference is now. I'm going to wait some time and see what the time difference is later. And I'm using my definition of frequency, not your definition of frequency, because I'm giving the talk. Okay. And so I'm going to measure the time difference now and the time difference a little later. And I'm going to essentially divide by that, blah, blah, blah. It's just algebra, and I'm going to figure out the frequency. So there it is. I measure the time difference. But because there is measurement noise, although my time difference is really this value, in fact, I could have found any value like that because of the measurement noise, of the phase noise in the measurement process. And now I do the same thing. I wait a little bit of time, I make the measurement again, and again, I have the same problem. And now if I wait some time tau, whatever it is, and now if I estimate the frequency, the answer is, although the red line shows the quote unquote true frequency, my actual measurement could deviate by the lines that I've shown. And that's because the uncertainty in the measurement process of the time feeds in to the calculation of the frequency. If you want to be fancy about it, you talk about covariance and blah, 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 but this is not the mathematics department. We're going to have to talk about covariance, okay? But the net effect of that is that the effect of a jitter in the time measurement has produced an uncertainty in the frequency estimate, which has nothing to do with the clock. In other words, if the management were to appear and say, here's $1, make it better, the answer is, if I take my $1 and improve the clock, I haven't done anything at all, okay? Because the process It's not a clock process, it's a measurement process. Okay, and that's an important issue to recognize because that's what happens. Okay, now let's suppose I said, right, what I'm going to do is I'm going to wait some longer time, and I'm going to measure. Instead of measuring at this point, I'm going to measure at that point. Well, if I measure at that point and I do the same thing, then you can see that the cone of uncertainty of frequency is smaller. And what that tells me is that the cone of uncertainty of frequency depends on how long I wait between the two measurements. And if I wait longer, if I can afford to wait longer, my uncertainty in the frequency due to the uncertainty in the time is diluted. And it's diluted by the averaging time. And you can do some algebra and figure out what it is. But the point is that there is an advantage to waiting. If you can afford to wait, then you can get a better estimate of the frequency. But of course, in the real-time world, you can't always afford to wait, right? That's a problem. Okay. Okay, so now what I'd like to do is, now I've given you kind of all of the good news and the bad news and the awful news and the whatever news. And what I'd like to do is I'd like to now show you some real data of what real clocks actually look like. Okay, so what I've done is, first of all, this is the offset. And now offset, as I've told you, has several meanings. In this slide, offset means frequency. And so what I've shown you here is the frequency of a clock. And this is a cesium clock. It's HP 2935. It's one of the clocks in this ensemble. And what it has is, it has a bunch of characteristics that are important. First of all, the average of the frequency is not zero. You can see that the plot has subtracted off an average of 2 × 10⁻13. And so that this particular device has a static frequency offset of about 2 × 10⁻13. And not only that, but it has jiggly wigglies that are fast, like this, and jiggly wigglies that are slow, like that. And so you recognize that all of the problems that I've talked about, in fact, are real world problems. Right? And so that's a typical cesium standard, and that's what it is. I have to live with that kind of data. Now, the scale, you can see that this is a few hundred times 10⁻17, which is a few times 10⁻15. So that the full period variation over this period, which is like whatever it is, 600 days or something, is like a few times 10⁻15. Now, let me show you, let me compare this with a hydrogen maser. So there's a, okay. So there's a hydrogen maser. And now you see immediately that these data look very different. This is not anything like the same kind of data. First of all, the dominant effect that you see in a hydrogen maser is frequency drift. And because a hydrogen maser, it turns out, has very, very significant frequency drift. That is, the idea that you're measuring something that has to do with the atomic frequency of hydrogen, well, that's not quite true. What you're measuring is some complication of the atomic frequency of hydrogen and the cavity that it's in, and the electronics, and yada, 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 blah, blah, blah. And I have to estimate the frequency. Well, for that, I have Tom Parker. And Tom Parker predicts, based on previous data, what the frequency is going to be, and that's his prediction. And it's not bad. Okay, remember that this is a prediction going forward. He doesn't have the luxury of having this data. He has to do it back here at the beginning of the plot. He has to project forward what's going to happen. And you can see that it's not terrible, but what I can do is I can characterize this thing and compare it to the previous one. And I played around with trying to show you the same plots on the same thing, but I couldn't make it work. So what I did is I wrote down here, I compared the various characteristics. And first of all, the drift. Well, the drift of the hydrogen maser is about 2.5 × 10⁻14. It's an enormous drift. Remember, the 10 to the minus 14 is a nanosecond per day. And so 2.5 × 10 to the minus 14 is 2.5 nanoseconds a day. And now, if you had a clock that was offset by 2.5 nanoseconds per day, and you worked for the time and frequency division, you get sent to bed without dinner. Okay, that's a serious issue. as you'll see in a minute, okay? And you don't like to get sent to bed without dinner, okay? But now, if you look at the offset, well, it's a part in 10 to the 12. It's more than a part in 12, which is much bigger than a cesium offset. So a hydrogen maser has two problems. First of all, its drift is super duper large. And second of all, its offset is super duper large. It's much larger than cesium. And that's why you don't use hydrogen for being a primary frequency definition, because the offset is way too large. Okay. On the other hand, the wander, that is the slow frequency drifts, well, it's much less. And the jitter, namely the rapid frequencies, this hair on the data, it's about the same. Well, why is the hair on the data about the same? Answer, because the jitter, the rapid fluctuations, does not depend on the clock, it depends on the measurement process. And the cesium and the hydrogen are both being measured by the same measurement system. And so what you're seeing is a thing which is limiting by the measurement system and not by the clocks. Okay? And so what we're going to do now is we're going to try and say, well, let me combine these data somehow. Okay? And in order to combine them, I'm going to use what's called an ensemble algorithm. Now, you got to remember that the ensemble algorithm has to pay attention to all of the bad news and all of the good news and all of the effects that we've talked about, okay? And so what I'm going to do is I'm going to construct a personality of each clock. And the goal of the personality is to separate the signal from the noise. It's to try and decide which of these effects is systematic and which of these effects is measurement noise or clock noise or frequency noise or whatever. And what I'm going to do is I'm going to use the personality to do the prediction, which I showed, kind of plots that I showed you. Namely, I'm going to sit at each time, and now I'm going to predict what's going to happen at the next measurement interval. And in the current time scale, the measurement interval is 12 minutes. And so at every time, I'm going to predict what's going to happen 12 minutes from now. And then when that time appears, I'm going to measure what happens, and I'm going to compare my prediction against my measurement, and I'm going to adjust my prediction to match the measurement as best as I can. Okay, so that's the goal. That's how an ensemble timescale works. Now, that sounds like an easy job, but of course, it's an undetermined process. I'm measuring time differences, and I'm trying to take those time differences and ascribe them to all sorts of stuff. And of course, I can only do that in a statistical sense. And I'm going to compute the weighted average, and the weight is going to be defined by the prediction error. That is, how well does my prediction match what actually happens? Okay, but I've got to watch out for measurement errors. Okay, because if I get a measurement error, I have to recognize that that's a measurement error, and it's not a change of personality. Okay, and now pay attention. The process can be circular. Remember that the way you analyze the data is that you construct a model based on the data, and then you turn around and use that model to analyze the data. And of course, you're chasing yourself. If you make a mistake in the personality, you're going to make a mistake in the analysis. And if you make a mistake in analysis, you're going to make a mistake in the personality. And the result of that is that a timescale produces a consistent picture of reality based on the best data that it has. But a consistent picture of reality is not necessarily the same as the truth. Okay, so now it turns out, what I did is I showed you that although hydrogen masers have all of these awful properties, in fact, the properties are predictable, so that the error in predicting a hydrogen maser over 12 minutes is a few picoseconds, 20 or 30 or 40, and the error in predicting a cesium standard is a few hundred picoseconds. And that's because although the hydrogen maser drift is very, very large and offset is very, very large, I can model them very, very well. And the result of that is that the prediction error is rather small. And so now we can talk about a real-time output. I have my 18-1 algorithm, I get the clock data, I get measured drift values from Tom Parker, and now I have an output generator, and that's called UTC NIST. But I'm going to have systematic errors that I have not dealt with properly, and that means that I need to do some steering. I need to correct my data based on something else. And what I use is the BIPM, the International Bureau of Weights and Measures. And now the BIPM has two timescales. One of them is called UTC, and it's kind of the official timescale, and it's available on the 10th of the month for the preceding month, which means that most of the time you're running blind. And then there's provisional UTC, which it calls UTC-R, rapid UTC, and it's available 5 p.m. Paris time through the preceding Sunday, which means that it turns out that it is very useful to look at all this data just before coffee time, just before cookie time for the physics colloquium. And so just before cookie time in the physics colloquium is when you look at this data and decide that a steering is needed. Okay. And how do we steer? Well, the answer is we can steer all sorts of data, blah, blah, blah. We can use this data, we can use that data, and each one of my colleagues has their own way of doing it. But I want to talk more about philosophy, namely, not what data should you use for steering, but what philosophy should you use for steering. And so here it is. Here is the real data for the last 600 days of UTC NIST compared to the BIPM calculation. And the verticals, this is like 600 days. Don't pay attention to the x-axis. The units are Julian days, and it doesn't matter. It's like 600 days, it's like 18 months. Okay, and so the y-axis is nanoseconds times 10, so that 20 is 2, and 30 is 3, and so on and so on. And you can say that we have managed to keep UTC NIST within, oh, I don't know, take your number, plus or minus 2 nanoseconds for a year and a half. And you can say, well, that is really wonderful, Judy. You've done a fantastic job. Okay, but before we get too excited, before we break out the champagne, let me remind you that that's not the only way of doing it. Okay, there's another way of doing it. Okay, this way of doing it emphasized time accuracy, but there's another way of doing it, and the other way of doing it is to emphasize frequency. And now let me take you back 10 years, and this takes you back to 2012, and I show you the same data, UTC NIST, UTC minus UTC NIST, and you can see that the data has very different character. Okay, first of all, the peak, that's 150, so that's 15 nanoseconds, and that's 20 minus 200, so that's minus 20 nanoseconds, but the data are smooth. There are hundreds of days where the slope is a constant. And what that means is that although I'm dealing with the fact that the time accuracy of UTC NIST is not correct, the frequency stability is just right. Okay, and now the question is, which one do you want? Well, the answer is in 2012, that's what we wanted. And now we want time accuracy. Okay, so let's summarize. Okay, so atomic clocks have systematic errors, they have noise contributions, they have a whole litany of sad stories. Okay, and a time scale is intended to compensate for the systematics and attenuate the noise. Okay, but the estimates are underdetermined. Okay? That is, you can't completely have a closed form solution. There are more unknowns than there are measurements. Okay, and so the long-term accuracy depends on steering. Okay, and you can steer for time accuracy, or you can steer for frequency stability, but you can't steer for both simultaneously. And as is usually the case in the world, where you stand on the question depends on where you sit. Okay, thank you. That's all. And I'd be pleased to answer questions, and anybody who doesn't ask a question now can always ask a question later.
So if you're in person and you'd like to ask a question, I've got a microphone that goes to the world, so please use that if you want to put your hand up. And if you're remote, we're watching the chat. Tyler McMacken here is watching the chat, and you can interrupt. Meanwhile, Dave Nesbitt has a question, which is about personality. What's the difference between personality and clock offset? And maybe I can phrase that a little bit. What is personality? Do you measure it on a 6-point scale or something?
No, the personality, that's an excellent question. The personality of a clock has a whole bunch of parameters. First of all, it has what I think of as the static frequency offset. That is, if the clock has a static frequency offset, that is part of its personality. I know that this clock gains 1 second per day, and I'm going to subtract 1 second per day from all measurements. The second thing is, does it have a frequency drift? Okay, that is that 1 second per day frequency value changing by 1 second per day per month, so that after a month, it's now 2 seconds per day. Well, that's part of the personality. Then I have statistical parameters. How well a measurement can I make? That is, what is the measurement noise? What is the frequency noise? What is the frequency drift noise? And so on. And so the personality is the ensemble of all these measurements, the ensemble of all these numbers. And I keep track of all of these numbers for every clock. So there's a table inside of the algorithm which has all of these numbers for all of these clocks. And these numbers are used to evaluate what the measurement is compared to what I expected.
Yeah. Other questions? We have one at the back. You'd like to say who you are?
Thank you. I'm Calvin. I work in the instrument shop, one of the staff members. You talked about in the 50s when there wasn't a very precise definition of the second decided on yet, and people are trying to decide what that should be using their individual measurements of the cesium transition. How do people compare their measurements of the cesium transition with each other without a second?
The answer is that at the time, there were two methods that we used even down to the era when I became associated with MBS. And the first one was portable clock trips. Okay, then you actually carried a clock from one place to the other. And now, to some extent, we're talking about distribution mechanism now. And so let me introduce to you the idea of common view. Namely, there is a system that generates ticks that may have nothing to do with the time and frequency division. And the only characteristic of that system is that the transit time between two places, between place A and place B, is the same. Okay? So it is logically midway between the two places. Then both of those places measure the tick, the time of arrival of a tick. And because the two transit times were the same, I can now take those data. This guy measures my clock versus the received signal, and this guy measures my clock versus the received signal, and now I subtract the two data. And that's called common view. And that was used back to, well, it was an old method when I started working on the business in the early 70s. It had been used for years with Loran navigation signals, okay, which are very big pulses which are used for navigation, and we can talk about that. That's a completely separate. But the point is that we're using common view. In fact, Dave Allen and I, we also looked at the question of using the time signals from channel 7 in common view. Namely, we would look at some piece of the picture of the signal received from channel 7, and we would do that here, and we would do that at Fort Collins, the radio station. And the transmitter was not equidistant, so we had to make a small correction for the fact that the signals were not the same, but it was the same idea of common view. Okay, so that allows you to transfer the time scale of one place to another place without actually knowing what's going on. And in fact, the generator does not even have to know that it's being used. So channel 7, although in fact it did know that it was being used, but it didn't have to know it. We could have used channel 7 without asking them, just by yielding with the signal. So the common view was the method of choice, and it's still a very widely used method, except now we use GPS signals, but it's the same idea. Okay.
Thank you.
Sure. And then now, in the end, of course, the common view has to transfer the data from somewhere, and so that transfers the data from a place like NBS or the Naval Observatory, which has some standard, which is now compared with some other standard, and so on. So for example, I carried a clock between Boulder and Paris, and so that it would be calibrated by what was called the Bureau International de l'Heure, which was before the BIPM. And it was a way of transferring the time scale of NIST or NBS at the time to Paris. And I stopped at Dulles Airport, And I was met by a representative from the Naval Observatory who carried a clock. And we did comparison, we did clock comparisons. Now, you recognize, or you might, if you think about it for a while, you recognize that there's general relativity associated with all of this, okay? But general relativity wasn't, the clocks weren't that good at that time. So we didn't have to deal with exactly all the issues of the clock going on United Airlines and what happens and, and all that kind of general relativity stuff, or even special relativity stuff. This was before the era where those kind of issues were important. And so clock transport is not used so much anymore exactly because of that, because you need the corrections of general relativity and special relativity.
Hi, I just wanted to ask, this is Graham Smith from JILA.
Sorry.
And my question is, what was the astronomical standard that people were using before these atomic clocks?
It was called ephemeris time. It was called, there were a number of different astronomical standards. The earliest astronomical standard was called mean solar time. And mean solar time was effectively the length of the apparent solar day averaged over a year. And that turned out to be not good enough. And so then it became essentially a time based on the length of the year. Essentially the time interval between equinox and the next equinox. And that turned to be that going enough. And in the time of Markowitz, when they did the comparison, the thing was ephemeris time. And ephemeris time means, let's suppose I write down what the orbit of the moon is supposed to be, and I parameterize the orbit of the moon in as a function of time, then that time is ephemeris time. And it's the time which, when I put into the orbital calculation of the moon, makes the position of the moon be what the position of the moon actually is. Now, measuring the position of the moon is a whole story all by itself. And all these things open up new colloquia, okay? And so how did Markowitz measure the position of the moon? Well, that's a colloquium all by itself, okay? Because the moon's a big thing. And what does it mean to measure the position of the moon? Well, okay, so we talk about that as or colloquium or whatever, but that was the way it was done.
Hi, Judah. Thank you so much for the very nice talk. I'm Anamaria Ray from JILA. And I'm curious, you talk about microwave clocks, but we know now that these are not the best clocks. So I would like your input of what needs to be done, or what do you think is the perspective?
I'm sorry, I can't quite understand.
You cannot understand.
Could you just repeat? I didn't quite understand the question.
No, so now all what you talk about cesium clocks or microwave clocks. Yes, so your talk was about microwave clocks.
Well, microwave. I'm sorry.
The cesium clocks are not the best.
The microwave frequency, microwave.
Yeah. So we want to make an optical transition.
Yes, but what about optical transitions? And what is your perspective of what needs to happen to make them the standard?
Okay, that is yet another colloquium. Okay, there is a committee of the BIPM which is looking at the question of the transition from cesium to some new standard. And there are two difficulties. The first is there are a whole bunch of research groups, and every one of them has their favorite optical standard. Okay, you talk to person X and he'll say, oh, you got to do with this one and got to do with that one and so on and so on. And at least at the moment, there's no clear winner. Okay, that is, there's not one that's so obviously better in the view of the entire community. I'm not talking about in the partisan view of the research group. Okay, so that in the view of the entire community, there's no obvious winner. And so the question is, well, okay, shall I make one of them be the main guy and the other one be the approved secondary representations? And that's one possibility. And that's in fact what happens with cesium now. There are approved secondary representations, which are regarded as equally good. So maybe that ought to be done. Or maybe we ought to have an ensemble average in which all the various groups get together and what becomes the standard is some average. And the answer is there's an ongoing discussion. The most optimistic number that I've heard is that there will be a change in 2036, which is, I don't know, whatever, 15 years from now. And now there are some people who say it's going to happen in 2030, but my guess is we're not going to be ready in 2030. The scientific community are not going to be ready in 2030. but maybe we will be. Okay. But the issues of, well, which transition should we use, and what about all the others? What about the secondary representations? And do we do an ensemble average, or do we just do one? And if you want to know more, I can point you to the BIPM, or we can talk about it offline. Okay.
Maybe actually I can ask a variation on Anamaria's question, which is what applications need something that is better than the cesium clock?
Okay, if you talk about practical applications, I'm not talking about scientific laboratories. I mean, I'm not talking, okay, the practical applications depend not so much on this on the cesium clock, on something better than the cesium clock, but they depend on something like international coordination and reliability. That is, for example, I make an international phone call and I have to hand off that call to a whole bunch of stations, and all those stations have to be synchronized. And I have to know where I am, and I have to know the position of the stations to something on the order of tens of nanoseconds. So it's not cesium quality. And in fact, most of these standards use rubidium quality. Okay, but for example, what you can think about, if you really want to think about it, is I want to transmit 60 hertz power from Colorado to New York, because at 9 o'clock, at 7 o'clock in Colorado, it's only 5 o'clock in New York. And so maybe in New York, I take the power that's being generated there, it's only 5 o'clock in the morning, and I transfer it to Colorado. But then, but wait, but the 60 hertz, what about the transit time? And how do I synchronize generators in Colorado and New York so that the power arrives in phase? Well, in fact, what does it mean for the power to arrive in phase? Okay, and you know, that's yet another colloquium. Okay, so that turns out to be, the tolerance turns out to be microseconds, 26 microseconds. And so there are very few applications that require nanosecond level accuracy, except for things like navigation, because the velocity of light is a foot per nanosecond. If I want to measure the position of something to a foot, I need to know the time to a nanosecond. And so, for example, to name a random possibility, if I want to take a missile and wind it up, and it has to wind up in a window, 5,000 miles away, I need to know the transit time to nanoseconds. Okay, so, but that's not an everyday kind of application.
Very much. We have
2 more minutes.
2 minutes. If somebody has a last question, Tyler, is there anything online that's happening? Any last question? Going, gone. Thank you very much. Let's.